Okay, so let's review a couple things from today's class. Here we're trying to figure out the percent by mass of water in the hydrate, which is given by the formula here, and also X, which is the number of water molecules inside the crystal of this hydrate. So remember that a hydrate is a crystal, it's a solid that contains in this case magnesium sulfate, 1 molecule, and X water molecules. And the goal here is to determine X. Obviously, X has to be an integer value because we can't have a fractional water molecule. It doesn't necessarily have to be 3. I just drew it in this schematic. A couple things here. We want to pay attention to significant figures because we're going to do so in the lab because that's going to be important. We also need to figure out what is the hydrate and what's the anhydrous solid. Anhydrous means without water. You may see that terminology. This is the anhydrous solid. This is the hydrate here. So you need to make sure that you don't screw up which one is which. So let's do the percent by mass of water first. We know the mass of the hydrate, that's given there. So I'm just going to note that this is 5.061 grams. To determine the mass of the water, we are going to need to subtract the mass of the hydrate from, or I should say the mass of the anhydrous solid, the MgSO4, from the mass of the hydrate. So I'm just going to put that there. From the conservation of mass, the difference has to be the mass of water. So let's actually put these numbers in and go over the significant figures. This is 5.061 grams. This is 2.472 grams. When we subtract, we keep the fewest number of decimal places. Since we have 3 decimal places in each, we will keep 3 decimal places. So here is the mass of water. So this is how much water was lost in this experiment, and we're ready to calculate the percentage by mass of water. This must be equal to the mass of water, which is 2.589 grams, over the mass of the hydrate, which is 5.061 grams times 100. Since this is a multiplication and division step, this is an exact number, it doesn't have significant figures, we will want to keep the fewest number. We have 4 here and 4 here. They were very nice in the significant figures for this problem because if you didn't know the significant figure rules, you'd probably still get the same number or the correct number, which in this case will be 4. However, I may or one of the teachers who you will have write the final exam, or you may have in a subsequent term, will certainly not be nearly as nice going forward. So the answer that I get here is 51.16% by mass of water. 4 significant figures, so about half of it is water. Let's move on to the next part. So now we want to find X, and we've already said that X is the moles of water over the moles of magnesium sulfate. So what I'm going to do is formally convert the masses to moles after I write the formula for magnesium sulfate. We already calculated 2.589 grams of water. Now, normally, since it's easier to truncate around the molar masses, I often do that for my calculations in class. Here, since I'm doing the lab situation, I want the most precision. I'm going to actually put the entire molar mass. You don't have to, but it's just what I do here. 4 significant figures in our measurement, so we're doing a multiplication or division step, so we're going to keep 4 significant figures here. So we have calculated that we have lost, in this case, 0.1437 moles of water. I'm going to do the same thing for magnesium sulfate, but not lead you through it. And you should feel free to check my significant figures there. X, therefore, is equal to 0.1437 moles over 0.02053 moles. Notice that our units for moles cancel, giving us a dimensionless number, or a number with no unit. And I get 6.998. Notice that the answer here is the 4 significant figures, 4 there, 4 there. This makes me feel good because we said that x should be close to a whole number. So therefore, I'm going to argue that the formula of the hydrate must have been with 7 water molecules surrounding it. And we are done.